Yeah, we're at 7:32. I would say we should start to roll, huh?
Let's roll it then.
I don't
First
see.
of all, welcome to everybody
I don't see
who
more.
is attending this February session for the Chester County Astronomical Society's meeting. Especially warm welcome to our members who have not been with us before, such as Randy Rainville, who's sitting up top there. Welcome to the club, Randy.
Who is the newest member?
Welcome.
Thank you very much.
And to Ardash Kataria. Hello.
Hi.
Welcome to the group.
I do. Yeah.
And of course, an especially warm welcome to all the affiliated and friendly clubs everywhere who are tuning into our meeting. Welcome. It's, again, a little bit frustrating to be having to do this in the middle of COVID, but we will keep everybody informed as to when we feel it's, and when the university is going to let us know when it's safe to actually have meetings back at Westchester again. And we'll keep you all posted as the situation evolves. It's still fluid. I really never thought with 2 years into this, we would still be having to change gears so often, but here we are. Is Dennis O'Leary on? I don't see him anywhere.
I don't see him. No.
That's too bad. I was going to wish him a happy birthday.
Oh, wow.
So I can't embarrass him tonight. Too bad.
Just 24 times 5.
So with that, Don, are we going to do a little what's up in the sky for the month?
Yeah. Yep. I will do a bit. Let me just one quick announcement. We are scheduling some public star gazing events for the spring and summer.
Yes.
I need to sort out dates for Hoops Park, and then I'll publish the list to all our members, and we'll get John to put things on the website. And also including a list of potential places to go camping this summer, like the York County Star Party. And for anyone can possibly make it, it's a long drive to West Virginia, but StarQuest at Green Bank Observatory is an amazing experience. So if you want to do a long drive, it is really a wonderful place to go stargaze and to see a lot of presentations. It's like 3 or 4 days of talks during the day and a speaker at night and stargazing.
But leave your cell phone at home. You can't use it there.
Can't use a cell phone. Nope, not near a radar telescope. Nope. So anyway, I'll be putting that out within a couple weeks. Our first event at Brandywine Red Clay is in March. I don't have the exact date, but it'll be it might be in the newsletter. I didn't check if John put it in the newsletter, but we'll be communicating it out. So, all right, let me share screen. We'll talk a little bit about what's up in the sky. All right, is everyone seeing Stellarium? Is that coming through?
Yes. Yes.
Okay. Well, I'm going to just focus mostly because, it's cold out and we're not going to be going out for long periods of time. So I'm just going to really look at the area of Orion. Okay. And it's probably the most identifiable constellation in the sky with these 3 belts, bright, shiny Betelgeuse and bright white, reddish Betelgeuse and bright white Rigel. Walk outside. Well, let's see. This is actually real time. It's right now. And this is looking toward the south. So all I can do is look. He's in center stage right now. The newsletter in January, I wrote about this guy. This is the coal car cluster. And if you zoom in, you can sort of see, if you think of a cart, here's the wheel, there's one wheel, there's the other wheel. This is sort of the cart. Other people say it looks more like an alligator, which I can see that. Here's the snout, and there's the legs and the tail. I kind of see a dog, dog nose, dog ears, dog tail. So I think it's more of like the dog cluster than the coal cart cluster, but coal cart cluster is a good name for it too. And this is probably easily viewed with the binoculars, just above probably the single greatest binocular object in the entire night sky anywhere, which is the Great Orion Nebula. And this will show up in binoculars, but I would really encourage you get the biggest telescope you can find and zoom in on this thing and just stare at it. It is an amazing sight in the telescope. These wisps. I mean, when you look at it, it almost looks like clouds around the moon. It's so bright. It's it beats everything else in the night sky for me. If it only weren't so cold out when it's out here at night, but that's the Great Orion Nebula, #1 for me.
Sit over here, please.
And then if you go further up, with binoculars, this is one of my really favorite objects. It has a colander number. I don't remember what it is, but from the 3 belt stars with binoculars, there's a really beautiful S-shaped curve here that curls around the stars. And that any pair of binoculars will show you that. That's really nice. You see a lot of pictures of these two things, the Flame Nebula and the Horse Nebula. You won't see these in a telescope. This kind of thing that Dave Hockenberry takes pictures of. But you won't see this with a telescope unless you're really out, maybe in Arizona or Cherry Springs with a 24-inch Dob. Maybe then you can pick it up, but not in our skies. I'll have to check this one out. Casper the Friendly Ghost Nebula. I've never seen that. I'm not really sure what it is. Must be an NGC. There it is. M78 NGC 78. Okay, it's a Messier object. I never heard it called that before. Another fun one, I think, is up here somewhere. Here it is, the 37 cluster. Now, it doesn't show up very well in Stellarium, but when you see the 37 cluster, it's right up in Orion's arm, where he's holding his club, right in his fist there. And you see this in the telescope, these stars do look like a 37. Can't really see it here, but you immediately say, yep, that's a 37. That's a really fun object to show people. Some other really nice ones in this part of the sky. The little beehive. We'll center that for us.
Oh, Valentine's, I see a heart shape.
Yeah, little beehive is a beautiful little cluster. And you may say, well, that's the little beehive. Well, why do they call it the little beehive? That's because over here
There it is.
in Cancer the Crab is the beehive cluster. And this would be really a binocular only object. It is so huge. I mean, it's bigger than multiple full moons, I think. It's really stunning. And like at a star party in the spring, you can pick it out just so the sky is not quite even dark. And it looks really nice with a very light blue-gray background. So there's another beehive cluster. I'm not sure which one this is. All right, M48. I was going to mention M46, 47, 48. These open clusters are all very nice. And they're easy to find one after the other. But I didn't know that M48 was called another beehive cluster. I don't know where Stellarium got some of these names. I'll have to look up Hadrig's Dragon Cluster. I'm not sure what that is. But we center on that.
Isn't Hagrid a character out of Harry Potter?
I think so. So I'm not sure what that one is, but Hadrig's Dragon Cluster. We're going to have to go looking for that some night. I really like to find open clusters on cold winter nights because you can get your binoculars, once you have them focused, you can go out and keep your gloves on and see a lot of these objects without having to grab an eyepiece and try to hold a telescope and try to get it aligned. I really like to focus on binoculars in the winter sky. And here's a new one to me up here. Was it Poor Man's Double Cluster? That we're going to have to research that and see what that is. But that sounds like a lot of fun too. Poor Man's Double Cluster. That's a new one to me. Now, if we go a little further up, probably the best single open cluster in the entire night sky, not too far from the single best nebula, is the Pleiades. These are the most lovely jewels in the sky. Oh, and the moon's out tonight. Not too far along through in the night sky. Can't be far from
A little less than a quarter.
must be first quarter, yeah.
That's about 40%.
All right, well, that's anyone have any questions on anything that's going on up there?
I got one comment.
Yeah, what's that?
I would love somehow or other to be able to visit some of these places.
Yeah. You got that right, Jack. Yes, you do. All right, well, I will stop the share. Let's see, is Morgan come on yet? I don't see her. Do you, Bruce or Dave?
Said she was going to join around 7:50 or so.
Okay, so we have a few minutes yet.
Few minutes, yeah.
Dave, you have to tell us a story.
It
What
was a dark
story?
and stormy night. No.
Well,
Oh, Roger signed on.
Yep, Roger's on. That's good.
He is.
I just saw on the news about a very large comet. But I don't know when it's gonna be visible. They said it's twice the size of Hale-Bopp.
Well, what I'll do for a second, since we have some time here, let me talk a little bit more about StarQuest at Green Bank. Everyone seeing my screen here?
yes.
Okay, so this is the website for Green Bank StarQuest. Want to be 10/17?
Yep.
Okay, so June 29th, July 2nd. To camp in the view of this thing is really, really special. That is the world's largest steerable radio telescope. You can do tours. Barb and I went up to this height or so. They flatten it out for tours. Roger and Linda went up to the very tip top. Now they closed that the day after. They were there ahead of us. They got up there. We didn't get up there. I don't know if Roger overloaded the elevator or what. I don't know.
Very funny.
No, there was
Tough crowd.
some maintenance being done, but it wasn't because of Roger. Sorry. And when you go on a tour, or if you're walking around it, you're not, of course, in the entire like 100 square mile zone around here. There are no cell phones allowed. They even want you. You can't take your phone with you to take pictures. They even ask you to take off a digital watch, so you don't approach the telescope. Even though it's down for maintenance the week of StarQuest,
They're
they're still doing some activities like in drift mode. So they don't even want a digital watch to be anywhere near this thing. There's a beautiful campground. You can see the science. There's a full science center here. Exhibits, beautiful lecture room, auditorium, and every evening there is a speaker. And then Saturday night is the main keynote address. They've had people like Alan Bean, the astronaut, give talks at this event. So I know it's a long way to drive, but I'll tell you, it's worth it. It really is. The schedule is starting to come into being. I don't think they have it out yet to speak of. There's a science center. Here's the actual telescope. Roger Lind, I believe, did do this railroad excursion, right?
And it's absolutely worthwhile doing.
Yeah. If you don't like to camp, there's a bunkhouse where you can stay at. Although I really encourage camping, because after the last presentation of the evening, everyone goes out and sets their telescopes up. And it's a very, very dark sky. I'd say it's pretty close, if not the same as Cherry Springs. So,
Yeah.
all right, well, I see Morgan's on now, so I'm going to end my share. And Bruce, turn over to you to introduce Morgan.
Well, I was saying to everyone at our little pre-meeting discussion that in my next life, I want to come back as Morgan Cable. She's doing all the cool things that I always wanted to do. So tonight we have Dr. Morgan Cable from the Jet Propulsion Laboratory in Pasadena. Okay. So Morgan is a research scientist and a group supervisor in the astrobiology and ocean worlds group. And she's actually an inorganic chemist by training and has gotten into astronomy and planetary science. She has worked as a project science engineer for the Cassini mission. She's also involved in the Europa Clipper mission, where she is a collaborator on the mapping imager spectrometer for Europa. that will essentially map the surface for searching for organics, salts, and minerals. And as she may talk about tonight, she's also a co-investigator for the Dragonfly mission to Titan. So one of the really cool things about Morgan's work, she works on organic and biomarker detection strategies, but in addition to that, she works on looking at quote unquote weird life and prebiotic chemistry. So in this regard, she and some of her workers were the first to actually discover crystals of essentially hydrated minerals on Titan that are made exclusively organic. And essentially they opened a whole new field of study just by this discovery, which is pretty remarkable. And in addition to this type of work, she also has explored a number of severe environments on Earth as analogs for other planets in the solar system. So for example, she's done research expeditions to the Atacama Desert in Chile, to the summit of Kilimanjaro in Tanzania, led researchers on expeditions to Iceland to study how life colonizes on fresh lava fields. So she's pretty much done the gamut, a really pretty rich and diverse area of research interests. But tonight, Morgan is going to talk to us about, I think, what is some of her major focus, and that is exploring the ocean worlds of the outer solar system. So with that, Morgan, welcome to Chester County Astronomical Society.
Oh my goodness. Bruce, that was a wonderful introduction. Thank you so much. Can you all hear me all right?
Yeah,
Very
yeah,
well.
Okay,
yeah.
I've got a new microphone, so I've been testing that out over the last week, but I hadn't yet tried it on Zoom. So very
question.
glad to.
Quick question before we start. How do you want to handle questions? Do you want to have them put them in the chat and then I relay them to you at the end to them, or how would you like to handle questions?
Whatever is easiest. I mean, I'm happy to keep this informal. We can all also do questions in real time. It's not going to trip me up. It's not like I have a script or anything. So
I muted everyone, so everyone knows you have to unmute yourself. If you want to ask a question, go right ahead. And then once the question's done, please mute yourself again so we don't get dogs and telephones and anything in the background, okay? All right, great. So if you have a good question.
Great. Okay, well,
go ahead.
Let's go ahead and get started then. So as Bruce said, I'm a scientist that's interested in exploring these places that we call ocean worlds. And I first thought that it might be important to explain what those are. So of course, our own Earth has many oceans. It is classified as an ocean world. But what we're finding as we explore further and further into our own cosmic backyard, our own solar system and beyond, is that Earth is actually more of the exception than the rule. Most of these other ocean-containing worlds don't tend to have that liquid on their surface. Instead, they have it underneath a shell of ice. And we found quite a few moons. This is not even a complete list, actually. This is already out of date. There is a moon called Ceres, or a planet called Ceres, a dwarf planet in the asteroid belt that also appears to have evidence for an ocean maybe in the late stages of its life. It also looks like maybe Saturn's moon Mimas, the one that we call the Death Star moon because it has that giant crater, may also fall on this list. But one thing that you can see is that most of these tend to be moons of Jupiter, Saturn, or even some ice giants like Neptune. And so this is a really exciting time to be a planetary scientist studying astrobiology, because as we all know, and as NASA's mantra has been for a while, is follow the water, right? Where you find water, you find life. And so if we're finding liquid water in all of these places, well, that gives us so many different opportunities to explore the potential for life to survive in all sorts of different conditions. And so it's a really exciting time to be in this field. Now, I don't have time tonight to talk about all of these, so I'm going to focus on these three, 2 moons of Saturn and 1 of Jupiter. And the reason for that is because currently, or planned, we have missions that are targeting these worlds, or that recently gave us a lot of data for these worlds. And so there are key places that we're planning on studying in this decade and beyond. So let's dive in. First, let's skip over to Saturn. So now we are instantly 10 times further away from the sun than Earth. Saturn is I had such an amazing opportunity to be involved in the Cassini mission just for the last couple of years of that mission's life in the Saturn system. And this is one of my favorite images. that Cassini collected during its, oh gosh, what was it, 14 years that it spent in the Saturn system. Was a really incredible mission. And to me, one of the key discoveries that Cassini made is actually in the background of this image right here. This is a snapshot of the south pole of a tiny moon called Enceladus. And I call it small but mighty because it is fairly tiny. It's about the size of the state of Arizona. But as a 5'2" tall person, small things can be mighty. And I believe Enceladus also fits that bill. What you're looking at is what we call a plume. This is material that is spewing out of these 4 giant cracks, these fissures in the southern pole of Enceladus. And we call these cracks a tiger stripes because it looks like a giant tiger just went and like carved out these cracks down in the south polar terrain. And what we're seeing is that there's a lot of material that is coming out of this these cracks. We see that they're a little bit warmer. This is thanks to a thermal imager aboard the Cassini mission. We were able to map out this terrain and identify that there are hot spots associated with these cracks. We're also able to fly through and assess the composition. Now, while Cassini is credited with the discovery of this plume, importantly, we have evidence now, thanks to some modern image processing techniques, that this plume has been active for much, much longer than that. In fact, Voyager, when it flew by about 1980, I believe November 1980, snapped this image. And this is Saturn here, and you can see this little spot is Enceladus. And if we zoom in, you can actually see, I hope you can see my pointer here, that there's just this little spit of something coming out of the south polar terrain. So while Cassini is credited with discovering the plume, it looks like Voyager did capture evidence of it as well. And we also know that Enceladus sits within its own ring around Saturn. We just happen to call it the E ring. The E doesn't stand for Enceladus. That was just the order they were discovered in, A through, gosh, I think it goes to F. But this material that's forming this ring, we believe is sourced from this plume. Now, where does the plume come from? Well, this is our current sort of slice picture of what Enceladus looks like. We have 3 lines of evidence that tell us that Enceladus has a liquid water ocean, a global ocean underneath a crust of ice. That ice is thicker at the south, or at this, excuse me, it's thicker at the North Pole, thinner at the South Polar terrain. And those cracks from those tiger stripes extend all the way down to that ocean. And I'll explain why we believe that to be true in just a little bit. We also have evidence for interaction of that liquid water with the rocky interior of Enceladus. And this is also important, we think, for generating conditions suitable for life. And so this makes Enceladus one of the most habitable environments that we've discovered so far. So let's talk a little bit about what Cassini found. Now, this is an example of one of the fly-throughs that Cassini did. We actually aimed it right at the plume, flew through this plume of ice grains and gas that's spewing out at 200 meters a second. And we feathered the important parts of the spacecraft. We used the giant high-gain antenna as a shield, and we flew through this plume multiple times. And this is an example of some of the data that we obtained. There were 2 important instruments that we used here aboard Cassini. One of them was called the Ion and Neutral Mass Spectrometer, or INMS. And what you're looking at here is a plot. Now, INMS is a mass spectrometer, and it's sensitive to small molecules. And so here, INMS was targeting water, which has a mass of 18. So oxygen is 16 plus 2 hydrogens for H2O gives you 18. And so this orangish line shows you how many water molecules that instrument detected as it flew through the plume. So this gives you an idea of what's in the vapor phase of the plume. Cassini also had an instrument called CDA, the Cosmic Dust Analyzer. And the best analogy I can use to explain this one is picture you're in a car and you're not driving, so you're a passenger. You stick your head out the window, and let's say that it's snowing, and you try to catch a snowflake on your tongue. That's kind of what CDA does, but it's going at about 5 kilometers a second. So at those speeds, whenever that ice grain or that snowflake hits your tongue, it goes poof. And when it goes poof, it generates ions, and all of the organic molecules, the salts, anything that's in that ice grain now becomes charged so we can detect it with a similar detector to what was in that other instrument I described. And so this instrument can tell you about what kind of grains, ice grains are there and what's inside them, which is really important. So these types of measurements Cassini made through multiple fly-throughs of the plume of Enceladus. Now the gas, we were able to determine that not only is there water there, but there are also some important things like CO2, methane, ammonia, and hydrogen. This is a plot showing some of those measurements as Cassini flew through in one of its plume encounters. Another thing that's important that we detected in the gas phase are some organic molecules. Now, this is exciting for us because life needs molecular building blocks to make, the stuff that's in our molecular machinery that is in our cells. And so it looks like these building blocks are present. Plus, we have that methane and hydrogen that I mentioned before. That'll be important, and I'll explain why in a little bit. That's essentially food for certain organisms. So that's in the gas. But in the grains, we also found some very interesting things. We found water ice. We also found salts that tell us that liquid water ocean is salty. And we also found something that we call HMOC, which stands for high mass organic cations. So these are positively charged, very large organic molecules. And we found these all the way up to the mass cutoff of the instrument, which tells us that not only are there a few organic molecules there, but it seems like there may be more complex species there as well. So this is very exciting for us because it seems like all of the things that life might need to eat or survive could be there. Now, not only that, but we detected these special nanograins. They're nano because they're nanometer in size, 2 to 9 nanometers in diameter, and they're made out of silica, SiO2. This is important because we have found in our own sea floor here on Earth, down at the base of the ocean, there are some environments like Lost City where we have hydrothermal systems that also seem to produce grains of this similar size and composition. Now, this gets us thinking of, okay, well, so not only is there liquid water, not only are there organic molecules, but there seems to be an energy source. Now, what do I mean by that? Well, there are certain organisms here on Earth that instead of using sunlight, as most plants do, and we actually derive most of our energy directly or indirectly from sunlight as well, because we eat the plants or we eat the animals that eat the plants. Well, there are some organisms that don't need sunlight. They do things like methanogenesis, where they use inorganic carbon, CO2, and generate methane. Or some other organisms will eat methane and generate other things. We call these chemotrophs or chemosynthetrophs. They're basically microbes that don't need sunlight to survive. They rely on chemical energy instead. And we think that these are the types of organisms that might exist in Enceladus's ocean. And we've done some modeling work based on the conditions that seem to be there from Cassini data that tell us that, yeah, these types of chemical reactions, here I've shown one that converts a carbon dioxide and hydrogen over to methane and water. And we found that these would be favorable in the conditions of Enceladus's ocean. So this is all evidence that suggests that life could exist in this ocean. And we think that it might look something like this. This is video footage of another hydrothermal system here on Earth. I would love for this to be of Enceladus, and maybe one day we will get there with a robotic submarine. But for right now, we just have Earth as an analogy. But you notice that not only are there microbes here, but there are more complicated life forms as well. You can see some shrimp, some crabs, maybe some octopods in these videos, but they're subsisting off of those microorganisms that are doing that chemical energy conversion. And so those are the types of ecosystems we think could be supported in these types of energy conditions that we find in Enceladus's ocean. Okay, well, how do we look for that kind of life, and how much life would we expect? Well, some scientists have taken measurements from Cassini and extrapolated that to how much energy there could be accessible for life. And that's what you're looking at in these plots here on the left, this global energy flux in watts. And then you can take that number and say, okay, well, if methanogens or other microorganisms like that are using that energy, well, how many of them would there be? And so that's what you're looking at on the right here in cell abundances. Now, the important thing to note here is that this y-axis of these plots, this is a logarithmic scale, and it's spanning many, many, many orders of magnitude. And this is because we don't have amazing data yet. We have not been in that ocean. We haven't collected samples to look for cells. So right now, we're basing this off of a lot of estimates. But one thing I will point out is that we have some examples of energy constrained environments here on Earth, like Lake Vostok. This is a lake that's covered up by ice in Antarctica. And it's kind of the best analog we can think of for a place that's completely cut off from sunlight and has some of these chemical energy using organisms in them. And it has pretty low cell densities, about 100 cells per milliliter of water. To give you an analogy, our regular oceans that are exposed to sunlight, they have about 10 to the fifth, so 10,000 or even 100,000 cells per mil. So we're definitely looking for less amounts of life, but still life could be here. And this is what helps us decide what kind of instruments we should bring with us, what type of sample processing or sample concentration we should do to be able to detect these trace amounts of life that we expect might be there. And so there are a lot of different mission concepts that have been proposed to explore the surface of Enceladus, its plume, or even to dig down and get into that ocean itself. But it's a very challenging environment. I mean, these are some digital elevation models showing what the surface of Enceladus looks like. And you can see these tiger stripe-like cracks. You've got to go up before you go down. They're more challenging than something like a Mars rover might traditionally be able to handle. And not only that, but how do you get to the ocean? Right now, we have two different models that fit Cassini data of what that crack might look like as you start to go down and try to reach the liquid underneath. One of them says, oh, it's just an open crack. It's probably 5 meters wide, and you could just go straight down, no problem at all. Another model says, no, hang on now. There's probably a choke point, similar to how a lot of our volcanic vents and things work here on Earth with magma, but instead of with hot magma, now we're talking about water. But similarly, you would have some sort of choke point. It could constrict on the order of tens of centimeters. That's a lot smaller. So how do you design a robot that could maybe get down into these environments? Well, I'm part of a team that has challenged ourselves to do that. And so this is something that we're working on developing here at JPL. We call it EELS, and you'll see why in just a second. We love our acronyms. EELS stands for the Exobiology Extant Life Surveyor, EELS, and it's basically a snake-like robot. And the reason for this is twofold. One, because it can move through really challenging and steep terrain, things that a traditional driving robot like a Mars rover couldn't handle. And also, its diameter is small enough such that it can move down that crevasse, that crack where the plume is coming out, and potentially even get down into that choke point, as you'll see in a moment. Now, the way that this robot works is it has these independently actuated segments. And you see those screw-like parts that are on each segment, those rotate. And so what happens is it can push against the walls of the crevasse and push down and go against those plume forces, which are pushing up at something on the order of, I think, 200 kilograms a second of material that's spewing out. This robot can push up against those walls and be able to move against those forces to get down to where the liquid is. As scientists, we really want to reach that liquid water because that's where we think the cells might be. That's where we think we're most likely to be able to find evidence of life. Oh, and it looks like I paused the video by looking at the chat. So there we go. Let's keep that going. And there's a question about contamination. Yes, that's a very good one. So we have a whole department called planetary protection, and they have two jobs. First job, make sure if we bring a sample back from some of these places, we don't, have the space flu come and kill all life on Earth. And the second job is to make sure we don't contaminate other habitable worlds like Enceladus with Earth life. And so we're currently working with planetary protection officers to be able to determine what the requirements would be for sterility assessment. Basically, how clean can we get a spacecraft like this so that we can guarantee that there could be no microbial hitchhikers on board? So that's definitely something that we're exploring as we mature this concept. So I've shown you a cool video. Actually, this video was generated by one of the animators who works on the Avengers. It's fun to be in the LA area. Sometimes you get to overlap with Hollywood. They also generated this sort of idea of how our ConOps might work. So the robot would have its own automated gates and something we call proprioception to be able to move and navigate in this terrain independently, because a one-way light time between us and Saturn, depending on where Saturn and Earth are relative to each other, it can vary anywhere from, I think, 68 to 86 minutes. And so it's not like we could just joystick this from Earth, doing real-time operations. This is going to have to essentially be able to move completely autonomously without a human in the loop. And that's another important part of our technology development efforts. So I've shown you these cool videos, but I figured I should actually show you a prototype. Otherwise, you wouldn't believe that this is more than just a sketch in computer space. So this is one of our first generation prototypes. This one was actually built primarily with 3D printed parts because this was in the height of COVID and we didn't have a lot of access to some of the machining pieces on lab. Since that time, we're now in the process of building what we call version 1.0. This is 0.0 or 0.1, I think is what we called it, to be able to accommodate payload. It's going to have a lot of imagers on it and be able to start to demonstrate some of that autonomous technology that I talked about. So this is really cool, and that's something that's in development. But now let's skip over 5 AU over to Jupiter. So we just half the distance between ourselves and the sun, going from Saturn to Jupiter. And let's talk about my favorite moon, Europa. Oh, and there's another question. Let's see. What temperature range will these robots diving into the oceans operate and be designed for? That is another great question. The surface of these worlds, like Europa here or Enceladus, tend to be pretty cold, on the order of like 70 to 80 Kelvin. So what is that in Celsius? It's like minus 193, I believe. And so they'll have to be able to operate initially in those environments. But once you get down to the liquid water ocean, or even in the plume itself, things warm up pretty quickly, right? Because of just the heat capacity of water as it's expanding adiabatically as it goes into space. And so it needs to be able to operate in, 4 degrees C kind of environments, all the way down to that minus 190 some odd degrees. So definitely an engineering challenge, but not something that we're completely unfamiliar with. We dare mighty things at JPL. It would ideally be able to take some samples to sip in some of that liquid, ideally filter a lot of that liquid. So we could filter, say, 100 mils or maybe even a few liters. So even if there's like 1 cell per mil, we could collect that and then analyze it with a whole bunch of biosignature detection instruments. And I don't have a lot of detail on that in this presentation, but I'm happy to talk a little bit about that during Q&A later on. Yes, I love Europa too, Susan. It's one of my favorite places. In addition to, I picked my top 3. That's what I'm talking about tonight. So yeah, it's Europa, like Enceladus. Also, we have evidence for it having a global subsurface liquid water ocean. And in the case here, it's really big ocean. This is, I think, 2 to 3 times the volume of all of Earth's oceans combined. So that's a lot of liquid water. It's underneath a shell of ice, just like Enceladus. Here, the shell is a bit thicker, but that doesn't mean that we can't see expression of that ocean on the surface. And that's something that we're very interested in studying. And we are currently building, actually, we're just about to move into phase D, which is integration. This is where we take all the instruments and we bolt them onto the spacecraft, and then we get ready for launch. So at the end of phase D and the beginning of phase E is when we will launch Europa Clipper and send it on its merry way to the Jovian system. Right now, we're planning the launch in 2024. And so that's only 2 years away. Oh my gosh, breathe. It's going to be fine. This is a really exciting mission. It has all sorts of instruments, including a couple that Bruce mentioned in the beginning. It's got an imaging spectrometer that'll be able to get us composition of the surface. It's also got very similar instruments to Cassini for being able to sample ice that is sputtered off the surface from micrometeoroid impacts. And also, we have tentative evidence for a plume at Europa too. And so if indeed there is a plume, we should be able to feather those solar panels, fly right through it, and collect measurements very similar to how Cassini collected them at Enceladus. So really exciting mission. I encourage you to go to europa.nasa.gov to learn more. We're going to learn so much with this mission. I mean, just the way that Cassini revolutionized our picture of the Saturn system, we're going to have that again with Jupiter, building on Galileo's amazing discoveries. Now, in addition to that, we also are thinking about what the next steps might be for continuing the exploration of Europa. And the next step, after you've mapped the surface, after you've identified key places that seem really interesting from a spectral perspective, is to land. Well, this is one of the highest resolution images we have from Galileo data of Europa's surface. Now, Clipper is going to get us much higher resolution data, but currently this is all we have. And each pixel in this image is 6 meters across. So what is that, like a school bus, half of a school bus? It's a lot. But we at JPL dare mighty things. And so we are currently working on a mission concept that could handle even the gnarliest terrain. We call this the Europa Lander mission concept. And you'll notice that when it lands, it has what look like legs. The engineers yell at me when I call them legs. They're not legs, they're stabilizers. And the reason for that is because once that belly pan hits the surface, those stabilizers will lock into place. And so even if the terrain is a little bit uneven or there's a big boulder or something around there, it should lock and keep that spacecraft stable. That's important because what you're looking at right here is an arm that we're working on developing to come out and cut into that icy surface. Now, remember, I said that these surfaces are cold. Europa surface is about 80 Kelvin. So ice at those temperatures is not like the ice in your freezer. It has similar properties in terms of brittleness and hardness to granite. Not only that, but metal tends to get brittle at lower temperatures as well. And so we have worked on all sorts of different alloys and cutting tools and techniques to be able to handle cutting into that surface without chemically or physically changing it too much, right? We don't want to heat it up. We don't want to allow any sort of chemistry to happen that could change our measurements and bias what we see. So this is currently being developed as a concept, and hopefully one day we will get additional support to be able to send this as a follow-on to Clipper. So write your congressperson and tell them that you want more missions to go to Europa. So there's a question about what is the source of energy on this world? Yes, on Earth, all life is ultimately based on the sun's energy. Technically, not all life, but most of it. Do you remember those hydrothermal vents that I was talking about? I could back up. So there are some images of them right here. These hydrothermal vents that we have at the base of our seafloor here on Earth, they're places where water is sucked into Earth's interior. It's heated up. It picks up all of these minerals, and then it spits them back out. And it forms these beautiful, very fragile chimneys of material. There are actually lots of scientists that think that this is where life originated here on Earth, because there are a lot of very eerie coincidences. Like some of the minerals that we see in these chimneys are carbon copies of some of the enzymes that are in your body right now in your cells, like the sodium, or what is it? No, the iron sulfur cluster, for example, in one of your proteins is identical to McKenna-white, which is a mineral that we see in these hydrothermal vents. It's creepy. But the point is that these vents, they have a lot of chemical gradients, like concentration gradients, temperature gradients, and they typically will spit out things like methane or molecular hydrogen that microorganisms can then consume and utilize. So these are these chemoautotrophic or chemosynthetic organisms that don't require sunlight. They are not living off of sunlight. They're living off of different energy sources. And these are the types of organisms we think would at least form the basis for an ecosystem in one of these worlds. So the last question was, do we expect to detect free oxygen as a life signature? Ooh, that is a good question. So one thing I haven't mentioned which you can kind of see at the top of this image here. You see these charged particles. So Jupiter, because it's sort of the bouncer of the solar system, it's the biggest planet, it's got a ton of gravity. It's also got a massive magnetic field, electromagnetic field. And so what happens is the solar wind from the sun, Jupiter will take those charged particles and it'll slingshot them around and then slam them into the moons nearby, including Europa. So the radiation environment on the surface is actually pretty intense. It's enough that it'll break up the H2O on the surface and break it up into H2 and O2. And so we actually think that some of that, if that oxygen gets down into the ocean, that could form a really nice, what we call a redox gradient, where you have oxidized things at the top, you've got reduced stuff from these hydrothermal vents, H2 and stuff spewing out of the bottom. And so it's basically a battery. And if life could take advantage of those redox gradients across that ocean, that would be a great way to sustain an ecosystem. So O2, we know is present there because of this radiogenic, it's what we call it, radio for radiation, genic for generating, for making these this oxygen from that radiation happening on the surface. So O2 itself might not be a biosignature, but there are other molecules that we might look for. Okay, so let's see. So we talked about Europa, we've talked about Enceladus. Let's get back to Saturn one more time to talk about one of my other favorite ocean worlds, Titan. Now, this is an image that Cassini took of Saturn, and this is to scale. That's how big Titan is. It's actually, if you count its atmosphere, it is the largest moon in the solar system because it has a very thick and very dense atmosphere, which is weird. Most moons, actually no other moons have that. If you strip its atmosphere away, Ganymede is a bit bigger, so we'll let Ganymede have a win because Titan is so cool by itself. It doesn't need to be the biggest moon. It can be the second largest moon in the solar system. That's fine. But it is fascinating. So it has this atmosphere. And in a few ways, it's actually similar to Earth's atmosphere. It's nitrogen rich. It's actually thicker than Earth's atmosphere. It also has some methane as well. And if you peer deeper through that atmosphere, which has haze layers. So here I live in Los Angeles. I'm used to haze. You all may not get quite as much. I think you have clearer skies than we do. But if you peer through the infrared, you can actually look at what Titan's surface looks like, as well as what's going on in its north and south pole. This is one of my favorite images that Cassini collected. This was collected by the visible and infrared mapping spectrometer. Excuse me. And what you can see here is this is a glint, a sunlight glint in the infrared off of something very smooth at the North Pole. Turns out that that is actually a lake made out of liquid methane and ethane. When I give talks to kids, I talk about lakes of liquid fart and they all get a kick out of it because that's essentially what it is. This is really exciting because this is the only other world aside from Earth that has liquid on its surface. It also has an ocean of liquid water on the inside. I won't be talking about that too much here today, but it's an ocean world sort of in two different liquids, which is very cool. So Titan has some analogies to Earth. It has a hydrologic cycle. So it's got clouds, it has rain, it may even have snow, but it's made out of different stuff. Water is frozen solid on the surface. So the liquid phase here is liquid hydrocarbons, methane and ethane, but they do the same things, right? They form these rivers that etch channels into the surface of Titan, just like we see on Earth. The scales may be slightly different, but the same processes are happening. This liquid pools in these giant lakes at the North and South Pole. This is Kraken Mare. It's one of the larger lakes. By volume, this is larger than some of our Great Lakes, right? This is a lot of liquid on the surface, but it's not liquid water. It's made out of different stuff. We also see evidence of dissolution. So places where that liquid has likely eroded away some of the surface of Titan, which, by the way, we still don't know what it's made out of. Because of all those thick haze layers, it was tough for Cassini to get any composition. So this stuff that we see here, these dunes that we see in the equatorial regions of Titan, we don't know what they're made of. We have some guesses. We think it's mostly organic stuff that's made in the atmosphere that then sort of deposits down. But we're not really sure what it's made out of. And that's one of the things that I'm studying in the lab, because until Dragonfly gets there in 2034, which is, yeah, don't do the math to figure out how old you'll be. You'll just get depressed. But until Dragonfly gets there, we have amazing capabilities in the laboratory that we can leverage to try to figure out what this stuff is made of, how it's forming these rich, diverse terrains we see on Titan's surface, and help inform what types of measurements Dragonfly might make and how it will interpret them. Okay, so this kind of looks complicated. This is our best guess of a lot of the processes that are happening in the atmosphere and on the surface and maybe the subsurface of Titan. And it's impossible, or at least really, really hard, to replicate all of these at once, right, in the lab. That would be a big challenge. So instead, as a chemist, what I do is I break this up. I'll pick one of these to study at a time and then see how it fits into the bigger picture. And so we started getting interested in these lakes or evaporite playas. And if you zoom in here, this is some other imagery from Cassini. You can see now this is a composite image that Vim's made, and the colors are not true colors to your eye. What you're looking at here is red, green, and blue, but here the red is 5 microns, so that's 10 times longer than your eye can see. The green is 2 microns, so 4 times longer than your eye can see, and the blue is 1.3 microns. And the reason we color code these is so we can, some of those are characteristic of certain organic things or salts or water that can help us identify stuff on the surface. And so that orangish stuff, that we call it an evaporite. We're actually not sure if that's exactly how it's formed by things evaporating away, but we see this in these bathtub rings around a lot of these lakes. We also see it in dried lakes. And so we were like, okay, what is that stuff made of? Let's figure that out. And so we go into the lab to do that. And this is an example of one of our custom cryostats that we've made. The nice thing about Titan is it's really easy to replicate in the lab. Titan's surface temperature is 90 Kelvin. And it's mostly nitrogen rich. So all we have to do is take liquid nitrogen, which is about 12 degrees colder than that. We make a liquid nitrogen bath, and then we just heat it up a little bit. And as that nitrogen starts to boil, it creates the atmosphere, and then it gets us right around to that 90 Kelvin that we want to get to. There's a question from Isaias about the origin of Titan's atmosphere. That is a whole debate that is going on in the community. Some people think that the atmosphere has been there for as long as Titan has existed. Some people think that it condenses out and forms this ocean of liquid nitrogen on the surface periodically. We don't know. One thing we do know is that the methane in Titan's atmosphere shouldn't be there. Over time, sunlight from the sun comes and it breaks up that methane and that nitrogen. And that's what we think is making all these complicated organic molecules that are on the surface. So that methane should have been destroyed in, I think it's about 100,000 years or 10,000 years, something like that. It should be gone. So the fact that the methane is still there tells us that it's being replenished somehow, maybe outgassing from the interior, which is really cool. So we're replicating this stuff in the lab. And this is another cryo stage that we'll use that can help keep things cold. It's got a nice window that we can do spectroscopy through. And so this is, I know this looks really complicated, but it's not that bad. It's just got lasers. It's got liquid nitrogen. It's got, you see this yellow thing right there? That is an HCN sensor, because one of the molecules that's present on Titan is hydrogen cyanide. And there's a saying, there are old chemists, there are bold chemists, there are no old, bold chemists. And I plan on living a long time. So that is to keep me safe, to make sure any hydrogen cyanide that's in this stage stays there and doesn't come out and try to kill me. So this day, I think we've got a gas bag hooked up. So this gas bag, I think, had a mixture of hydrogen cyanide and something else, maybe ethane. And we use that to squirt stuff in. It condenses inside of the stage, and then we can look at it with this fancy instrument, which we call a Raman microscope. It's basically a way to fire a laser at what that stuff is, and it tells us what it's made of and the kind of chemical environment it's in. And it also has a microscope attached so we can take pretty pictures. So this is an example of one of the experiments that we ran. This one we ran a few years ago. What we did was we took benzene. Benzene, you may be familiar with. It's a liquid on Earth, just normal temperatures and pressures. It's really bad for you. It causes cancer. It's abundant on Titan, and it's a solid on Titan. And it's not very soluble in methane or ethane. And so we figured, okay, well, if those bathtub rings around the lakes are made out of anything, it's going to be something that's going to crash out first. As soon as that lake starts to evaporate away, the least soluble thing should precipitate out. And so that's what we looked for. And so we started playing around with benzene and ethane in the lab, and we noticed something happened. Now, this is really weird. After about 15 minutes, we noticed that these big, chunky crystals on the left over here broke apart into tiny little crystals on the right. You see that? Now, this is really odd. Typically, when you are operating at 90 Kelvin, 100 Kelvin, really cold cryogenic temperatures, stuff doesn't spontaneously just happen. Typically, chemistry slows down. Sometimes it stops completely, but you don't ever expect things to spontaneously happen after 15 minutes. This was really weird. So we're like, what is happening? What's going on? Let's study this further. Well, we took that fancy Raman microscope, and you don't need to understand too deeply exactly what this is, but this was firing that laser at our sample. And what we get is we get peaks for different vibrations of the molecules inside. And so what you're looking at here is these peaks over here correspond to the carbon and hydrogens wiggling around in ethane. And then over here, you're looking at those carbons and hydrogens wiggling around in benzene. And what we noticed was that after that change had happened, that recrystallization had happened, we saw a new shoulder grow in, boop, on this ethane peak right here. Now, this technique not only tells you what's there, it also tells you the chemical environment those species are in. So this tells me that there is some subset of that liquid ethane that is in a different chemical environment than the rest. Not only that, but we saw shifts in some of the benzene peaks. So whatever's going on with ethane is affecting the benzene too. Okay, well, these are the two building blocks we have, right? We've got benzene, the 6-membered carbon ring, and we've got ethane. Well, how could these two interact in a way that would cause those shifts to those peaks that we saw? Well, we went back and looked at the literature, and there was a dude back in 2003 who found something called a co-crystal that involved benzene. Now, this wasn't with ethane, but it was with ethane's cousin, acetylene. Ethane has single bonds. Acetylene is the same 2-carbon structure, but it's dropped a few of its hydrogens, and it's got a triple bond between those carbons instead, but it's about the same size. And so we're like, okay, so maybe the benzenes are stacking up like dinner plates, and they're forming this thing that we call a co-crystal. And so, well, how do we study that? Well, we have some friends. This was pre-COVID time. So we went down to Australia and used what's called a synchrotron to fire X-rays at these crystals we had made. And based on how those X-rays bounced off, we were able to get a crystal structure. This is what that structure looks like. And so you can see the benzenes here, and then this flower-like thing, this is actually that ethane molecule, but it's like pointing out of the screen at your face, which is why it sort of looks like a flower instead. And so we found what is the first example of a mineral on Titan. And you can think of this as like a hydrated mineral, except on Earth, the hydrated would be because of water, but on Titan, the liquid phase is ethane and methane. And since ethane's in the crystal structure, this is like a hydrated mineral on Titan. Cool. What does this mean? Well, this tells us that there are ways that these molecules are interacting that is different than if you just had the pure molecules themselves. And here, this is an image that my colleague Mike Malaska made of that same crystal structure where he like draped a cloth over the benzenes. So you can better see what's going on with these ethanes, the flower-like molecules that are stuck. They're in these like tube-like structures. And this mineral is important because this may be a way that liquid ethane can be sequestered and stored away. This structure is more stable than just pure liquid ethane by itself. And so this got us thinking, well, maybe molecules like this or minerals like this, they may be important for how we think about chemistry and the potential for life in cold environments like this. Where before we might have been thinking of, okay, well, for life to exist, you need to have covalent bonds, right? Those are the kinds of things that are made and broken whenever our molecules need energy, right? With like ATP, with the molecules that are the energy currency for all known cells here on Earth. But on Titan, covalent bonds are super strong because the energies are it's so much colder that you need more energy to break those. Instead, we might look for weaker bonds that may be more important at Titan temperatures. And so it's caused us to rethink about how chemistry might happen, how associations between molecules might happen that could lead to maybe biochemistry at some point that might involve structures that would be very different from what we might consider for searching for life if we're biased by Earth perspectives. Okay, so we've got this hydrated mineral, but is this the only one? Or are there other Titan minerals? Well, since that time, we embarked on a quest and we have found a bunch more, which is really fun. They all look very different. They all behave very different and could form in different places on Titan. Some of them involve really gnarly organic molecules, things like acetylene. If anyone has used an acetylene torch, yep, that's the fuel. Some of them can involve more benign things like carbon dioxide, and they have very different structures, just like the diverse array of minerals that we have here on Earth. But it's just the rocks are made out of different stuff on Titan, which is really cool. One of the fun experiments we like to do as we're characterizing these is we'll expose them to a Titan rain event. And so what you're looking at here is that first flush is a gas of, let's see, today, I think that was acetylene and ammonia mixed together. So they make a Titan mineral. And that's what that beautiful snow is that you can see right there. So we'll pretend like that condensed out of the atmosphere and deposit it on the surface. Well, now let's make a flood of liquid ethane that'll just flood over this. And that's what you're seeing right here. So we just made a rain event on Titan. So that's liquid ethane. And we've dropped that liquid on. And now we would study this with our fancy Raman microscope and determine, okay, well, is that mineral still there? Or did some of it wash away? Did it destabilize because of that rain event? And this tells us how likely we are to find these types of minerals on Titan, or if they might be stable on, say, geologic timescales. And that can help us understand the geology and the mineralogy of this unique world. So things are starting to get interesting. So far, we've detected quite a few of these minerals. There's the one that I introduced you to that's equivalent to a hydrated mineral on Earth. There's one that is made out of the two most abundant solids on Titan surface that we think are there, acetylene and butane. So this one could be all over, which would be really cool. There's that one that I just showed you for a Titan rain event. This one might be linked to if there's any cryovolcanism that's releasing ammonia-rich liquid from Titan's interior. There are others that may make up this funky terrain that we call labyrinth terrain that we think is made out of something that can be easily eroded by liquid. There could be some places that are definitely not stable if there's a rain event. So we might only find them in places where things have been very dry on Titan for a very long time. There are some that may even form ternary complexes. We have some tentative evidence for some of those. And this guy is actually only stable for about 17 minutes. So if we find this, that means that there was a really recent deposit of CO2, maybe from outgassing from the interior. And here's one that we think we've got tentative theoretical evidence for that could be a ternary complex. So there are a lot of different things we can explore. And so these may be abundant on Titan. We're just scratching the surface, literally, in terms of what we can do with them in the lab. They have very different properties, and this is important for us to understand for how Titan may be evolving and what Dragonfly might encounter. And so this is the picture of where we think these could be forming or could be most prevalent in Titan's atmosphere and on its surface. And boy, it would be so nice if some mission was going to go here and land in different places and look for these sorts of things. Oh, yes, Dragonfly. So I am just so excited and fortunate to be a member of the science team of this mission. This is a big rotorcraft. I don't know if you all have seen the 2-scale images of the Mars rovers, Perseverance and Curiosity. You know, they're the size of a car, right? Like a Mini Cooper. This is the same size as those. So picture a Mini Cooper, take the wheels off, give it skis, and give it 8 helicopter blades. And yes, that is what Dragonfly is. The only reason this works is because Titan's atmosphere is so dense and its gravity is less. It's about 1/6, 1/7 Earth's gravity. Because of that, it's really efficient to fly. You actually don't need a lot of sort of downward force to be able to get airborne. And so because of that, it's actually more efficient to do these flying hops that Dragonfly is planning than it would be to just drive like a traditional rover would on the surface. And so the goal is to land near a crater on Titan's surface that's had a lot of this surface material excavated out, so we can look at what the bedrock looks like, and then we'll hop over and we'll look at some dunes and some interdune materials. So we'll get a sampling of all of these fascinating diverse terrains on Titan's surface. And we'll also be able to take measurements in flight, do some atmospheric measurements. We're going to give you a weather report from Titan, which will be really exciting. Here's the whole list of the payload. So we'll have mass spectrometer on board that can tell us what that surface is finally made of. We're finally going to be able to know what organic molecules are there instead of just guessing. We're going to be able to get the bulk elemental composition as well, get that weather report with the meteorology package, and take a ton of pictures, including we're having it's not necessarily a microscope, but it's a micro scale imager, similar to if any of you are familiar with the MALI camera, the Mars Hand Lens Imager aboard Curiosity and Perseverance. So we'll be able to look at some of the grains as well. I know I've kind of rambled on for a while. I want to make sure I leave a lot of time for questions. So I'll just quickly say that we've got a really cool strategy for scoping out future landing sites before we actually go and land there, so that we can make sure that we assess it for safety as well as scientific interest if it's a cool place to go to. And if you're interested in learning more, I've included the link down at the bottom, and I can drop this in the chat as well. So all the things I've talked about, none of this is done in a vacuum. Clearly, none of it is done by myself. These are just a few of the people who have helped with a lot of the work that I talked about today. And with that, I'm going to stop, and I'm very happy to answer any questions.
Morgan, this is Bruce. Thank you. That was amazing. Thanks so
Oops.
much. Kind of two related questions. Based on what you know so far, the lakes on Titan, would you predict, especially given proximity to Saturn, that there are tides in those lakes if they're suitably large, or is that not been known?
Yes, we actually have evidence thanks to Cassini. So one thing that Cassini could do is it took its synthetic aperture radar, or SAR, and as it was doing flybys of Titan, was able to bounce that radar signal off of not only the surface of the lakes, but also they were able to get a secondary reflection from the radar signal going down to the lake bottom and then come back up. So we know the depths over a lot of transects of the lakes. We know they're on the order of, say, 200 meters, 300 meters deep. And we did a couple of transects across. There's this one place, actually, let me see if I think one of my images might have it. It's called the Throat of Kraken. I think, hang on, let me share my screen again. So where is it? Yeah, here. So Kraken Mare actually is connected to another lake called Ligeia Mare, and there's a place where the flow is kind of constricted, and we see evidence of turbulent mixing and all sorts of things like that right at that Throat of Kraken. We also see, this is really cool and really weird, all of the lakes, even the ones that are not connected to each other by like channels, are at the same elevation, even if the surface, the surrounding surface, is not the same elevation. That tells us, we think, that all of the lakes are connected by like sort of an aquifer like subsurface reservoir that is keeping all of the lake levels the same, because it's all sourced from the same liquid underneath, which is really cool.
Can I have a follow-up
Isaiah
question?
he's asking the great questions. Go ahead, Bruce.
The second one, you were describing the various kind of hydrated hydrocarbon crystals that you've been working with and simulating and studying in a laboratory. Have you then simulated the kind of, let's say, radiation exposure or even magnetic fields that they may be exposed to, and see, again, how do the physical chemical properties of those crystals in a laboratory obviously change? And again, what would that inform you?
That is a great question, Bruce. So we talked about radiation as being important for Europa around Jupiter. Luckily, Saturn, the environment is much more benign. And plus, Titan has a very thick atmosphere that tends to block a lot of radiation as well. And so things are really mild at the surface. Actually, you would probably, you'd freeze to death in a few seconds, but radiation wise, you could handle that exposure for a very long time. You could live comfortably. And interestingly, since Titan has a thick atmosphere, you wouldn't need a spacesuit. You would need a heck of a parka, like you could not have any skin exposed, and you need to bring your own oxygen, but you would not need a spacesuit, which is kind of an interesting thought.
No. Thank you.
Yeah, so I'm seeing a few more questions in the chat. Let me see if I can get to a few of these. Which of the co-minerals would make the best rocket fuel? Yeah, awesome question. So ethane, certainly, that's a good one. And acetylene, it burns really well. So that might make a very efficient rocket fuel. In fact, I believe Titan has more hydrocarbons than all of Earth's oil reservoirs combined. So I keep saying we need to get ExxonMobil and all these guys. We should just get them to sponsor a mission, right? Like what are we doing? We should just take advantage of that. But certainly that is something that we discuss a lot when we're considering what we call ISRU, in situ resource utilization, for either these uncrewed missions or ultimately to send people to some of these places. Certainly the cruise to Titan is long, right? It's about 7 years. So that would be a pretty big ask, but who knows, down the line, it could actually make a nice environment. You've got liquid water. Once you melt the ice, you've got hydrocarbons for fuel, potentially to even use for organisms to metabolize. So there could be ways that you could sustain a human presence in a world like that. Of course, there are challenges. I'm really glossing over some key technology challenges, but it's not unfeasible. Let's see. Of all these places, which would be my top candidate? Oh, Isaiah, you're making me choose. Why? I think in our lifetime, Enceladus is unique because it's the only place where we have free sample spewing into space from the liquid water ocean underneath. And I think that is something, if we really want to look for life, that is top of my list for that reason. But I think it's important to study all of these worlds because we classify them all as ocean worlds, but that doesn't mean they're the same. Each one of these is incredibly different, has unique chemistry, has unique geophysics, and all sorts of other processes that are going on. And if we really want to search for life and understand the potential for life, not only in our own cosmic backyard, but beyond, we need to understand the spectrum of habitable environments. And by studying each of these different places, that helps us understand that. One other thing I didn't get a chance to mention is this is kind of cool from a cosmic perspective. So our star, the sun, is not the most common star in the galaxy, right? In the Milky Way. The most common star is actually a red dwarf, right? And you all I'm not an astronomer, so please correct me if I'm using the wrong terminology, but it's the most common star is much dimmer. And so any planet that is in a stable orbit around a red dwarf, so not too close that it gets coronal mass ejections or is tidally locked, but is a little bit further away, it will get a lot less sunlight than Earth does. In fact, it gets about the same sunlight as Titan does here in our solar system. So that means statistically out there are probably a lot more Titans than Earths, because there are a lot more red dwarf stars for it to be orbiting than there are stars like our sun. And so if we are able to deeply understand a world like Titan and its potential to have life, that can help us understand how common life might be in the galaxy and in the universe, which is really cool to think about. All right, the Jovian electromagnetic environment, Randy's asking for surface, subsurface chemistry. Yes, I touched on that briefly when I was talking about how the H2O ice at the surface is broken up into H2 and O2. And what happens is, hydrogen, molecular hydrogen is very light. It's the smallest molecule that exists, right? Two hydrogens stuck together. It's so light that it escapes. And so what you see on Europa is we don't even call it an atmosphere. We call it a tenuous exosphere of oxygen that's there. And so the theory is if there's any overturn or ways for that oxygen rich exterior to get down into the subsurface ocean, that would be your source of oxidized material. So oxidized is electron poor, reduced is electron rich. And so what you would have is at the top of the ocean, so the ice ocean interface, you would have an electron poor environment, so an oxidized environment. Then down at the seafloor, down at the bottom of the ocean, where you've got the hydrothermal vents and that sort of stuff, that tends to be electron rich. So you have electrons here, you have a dearth of electrons up here, and life can just act as a shuttle for those electrons and just have a little tax, an energy tax that it puts on it for taking those electrons and moving them up to the surface. And that's basically what chemosynthesis is. That's how a lot of these methanogens and those kind of organisms operate, is by doing that type of chemistry. And so that's what we refer to as the battery that could exist in Europa's ocean. And so, yeah, it all, of course, is reliant on those oxidants getting down into the ocean. And that's something that Europa Clipper will really help us understand, because it's going to give us a much better picture of the thickness of the ice shell, the thickness of the ocean, how old the surface is. The average age of the surface of Europa, we think, is about 50 million years, which is really young in geology perspective, right? Like that's younger than the age of the dinosaurs. And so we know that surface is being refreshed somehow. And so understanding that more deeply is a really important part of the Europa Clipper mission, and will inform subsequent missions like Europa Lander and others that we're hoping to continue to send to that fascinating world. I hope I didn't inundate you with too many cool things all at once. It's really exciting to get to work on all of these things.
A question on the Dragonfly. What are you going to do to keep that thing from landing in a puddle or getting rained on or something like that? I mean, is it going to have some sort of protection or a little umbrella that goes up when the rain comes over it or something?
No, that's a great question. And one thing, let me go back to that image of Dragonfly real quick so you can see what it looks like, because there is one important thing that I want you to notice here. Do you see any solar panels on this? No. Do you know what this is in the back here? Do you see where my cursor is pointing?
Radioactive storage.
Radiothermogenic.
Exactly. That's where the RTG is. Now, this is largely because of the fact that there's, the solar energy, sunlight drops as 1 over the distance squared, right? So you get 100-fold less sunlight at Saturn than you do at Earth. And plus the haze layers on Titan make it really challenging to operate with solar. And so instead we have this RTG. The RTG is great because that means we don't have to worry about operating day versus night. It also means that we have a lot of waste heat that we can use to heat the spacecraft. We don't want to heat the skids that are in contact with the very cold surface, but luckily, the triple point of methane and ethane is really close to the surface temperature. I think it's around 93, 95 Kelvin, something like that. Maybe it's 97. And so we just need to heat things up a little bit to not have to worry about essentially methane or ethane, rain or frost or anything like that accumulating. But there is a concern about what happens if we could get stuck. And so a lot of work right now is going into understanding surface properties. And that's part of why our lab work is so important. So that, as we touch down, we want to make sure we don't sink. We want to make sure we don't stick. And so careful selection of landing sites is going to be an important aspect of that mission. It's a good question. But we're not going to know if we don't go. So we need to go.
Is it something you can simulate in the test chamber?
Yeah, I have a question for Dr. Cable. Would the same energy source apply for the EELS device? And sort of a follow-up question. It looks like a device like that would require a substantial amount of torque to drive itself through some of this material. So that implies that it's going to have probably a series of motors at each joint. And then would the power source be stationary on the surface and then have some sort of like an extension cord?
Frank, you hit the nail on the head. Yes, that's the current plan. So Dragonfly is RTG powered because it is not going to visit any place with liquid water. Planetary Protection tends to get their panties in a bunch whenever you talk about taking an RTG anywhere near liquid water, because it could essentially that there's a risk of transferring organisms, and it could also like melt through any water ice if you're right next to a potential reservoir that could be habitable. And so eels is not going to be RTG powered. Instead, we might either keep that on the surface or have solar power or something else, and then have a tether. And the tether would, there are a lot of technology developments right now for very light, strong tethers that could be on the order of 1 kilometer or longer that would also transfer power. And so that's what we're currently looking at. There could be future versions of an eels-like robot that would have their own power source. In theory, you could do RTGs, but we need to understand very well how that would interact with the liquid environment and be very careful to not contaminate that habitable zone, right? That's the key problem. And so right now that mission concept is baselining having a lander on the surface, having a tether. And the nice thing about that is you get power down to eels and then you get the data back up. So we don't have to worry about having to climb back up the vent to transmit our we found life civilization level science back to Earth, that we can just send that back up to the landed element on the surface.
Thank you very much. Thank you.
Yeah, it's a good question. All right, there was one other question, I think.
I have a quick question.
Go for it.
On the eel, are the screw elements that give it traction, are they in counter-rotating pairs?
Yes, they are.
Okay.
Great question.
Otherwise it's spin around, right?
Exactly. Yeah, the engineers they're super creative with how that can work. And so you can operate them in counter-rotating mode, but then there's also a way, and I don't have, I will send you a link because I think there is a publicly released video from a lecture that Kayland Carpenter and I gave, yes, back in 2019 that shows this, but it can also become a self-driven screw. So you can have all of them operating in the same. And so what you end up having is like different forms of locomotion where the whole robot can straighten out and then it'll just sort of inchworm forward, but it doesn't move. Like it's just those screws that are moving around it to move forward. Then it can also have gates where it can sort of sinuously move around if there are large boulders or other obstacles. And it can also get you through what we call unconsolidated media. So that those plumes, the plume at Enceladus, about 90% of all of those little tiny ice grains, they fall back down onto the surface. And some scientists think that there's enough heat that they would sinter together and form like a creme brulee layer. And some other scientists say, no, there's not enough heat there. They're going to stay loose. And so you can think of this as like trying to move your way through a sand dune that's made out of ice at 70 Kelvin. So really, really cold. And so the nice thing about those counter-rotating screws is they can also move you through this like loose bed of sort of sandy grains. Because we're also, I didn't mention this, the gravity at Enceladus is very small. It's 1% Earth gravity. And so things are sort of, you can picture how the astronauts kind of had to hop on the moon. That's 1/6. So that's what, 15%-ish Earth gravity. Divide that by another 15 times and think about how you would move in that kind of environment, right? And so at some point, we're going to do some probably vomit comet tests or something similar in those gravity environments so that we can understand how those gates will change in the very, very low gravity environment. I hope I answered your question, Don. That was a good one.
You did. Yep. Thanks.
And I dropped a link into the chat for an hour-long lecture that Kayland and we did a tag team talk for a Caltech. KISS is the Keck Institute for Space Studies, and they host lecture series. So I encourage you to check that out as well. There should be some other videos that I didn't include in this presentation.
I'll send that link out to everyone after the
Please
meeting.
do.
Morgan, I actually had a question that was a follow-on to Don's. It was about the eels. So based on what you just said, where and when will like a prototype be tested on Earth? Like where are you going to do that to simulate the different gravity environments and stuff? How are you going to do it?
I just had a meeting about that right before dialing in to see you all this evening. So we're right now working with some colleagues up in Canada because not only do we want to do a technology demonstration to like prove the robot can work, but as a scientist, I would like to do some meaningful science wherever we're going to test this thing. And it turns out there are these very cool glaciers. There's a glacier called Athabasca Glacier in British Columbia, Canada. And most glaciers have these structures that are called moulins. Have you heard about these? They're super dangerous. They're basically just like holes in the glacier where water flows down in. And if you're a human, they're really dangerous because if you fall down one of those, you basically get sucked down to the bottom of the glacier and they never find you again. But they're also really great testing grounds for robots because we can push up against the walls of the moulin. It's just like a chimney, right, in the ice, and we can go down and explore. And it's also a great opportunity to do some earth science. One thing we're planning on doing is taking this, here, let me send you a link for it. There's this really cool team in the UK who've developed this instrument package they call a cryo egg. And I've just dropped a link in the chat to one of their papers. That it's basically, it looks like a white egg. It's a polycarbonate or something shell, and inside it's got a pressure sensor. You can also do temperature, salinity. There are a few other measurements you can include as well. And they're interested in deploying these kinds of sensors down in the base of a glacier because that can tell you about how that glacier is melting, where those subglacial channels are going, and it can inform things about just global climate change and how things are warming and all sorts of stuff like that. And so we've been collaborating with some earth scientists who are studying that glacier to see how best we can use eels to get to places that are too dangerous for people to go. And so right now we're planning, our first campaign is hopefully going to be this fall. There are certain times where it's good to go on a glacier and certain times when it's bad, depending on how much snowpack there is versus how much meltwater there is. And so we want to hit it at the right season.
Thank you. Thanks very much.
Great question.
One more question. Let's
Sure.
let's just speculate that in the future, you are wildly successful beyond your imagination and you find life there.
Okay.
At what level of sophistication of the life that you find would you feel comfortable continuing to explore, and at what level would you say, hey, we have to pull back and let this evolve on its own?
Oh, that's a wonderful question. Well, okay. I'm assuming this would be after I become world famous and collect my Nobel Prize and all of that. Yes. Okay.
Before or after, it doesn't matter.
Yeah, right.
Well, I mean, it would be a foundational, like these kinds of discoveries. It's really just a privilege to be at a point, and just so lucky to be at a point where we have the technology and the capability to access these environments to actually address this question. I mean, the last time we tried this on Mars was with the Viking landers, right? And they actually had 3 independent tests for life. One was positive for life, one was negative, and one was ambiguous. And so where does that leave you? I can tell you where that left us. That basically meant no more astrobiology missions for the next 35 or 40 years. We're just now getting to the point now where NASA is, and the community is saying, okay, we're ready. We've sorted out the issues that we thought we had with Viking. Those were all tests on sort of metabolic things. So taking some Mars dirt, squirting some water on it, and then see what gases come off. And it turns out that, you know, life can generate some gases if you do that kind of experiment, but there are also abiotic chemical reactions that can happen too and generate the same things. So as we design instruments and tests to search for life in these environments, we are trying to be as agnostic as we can. So not looking just for Earth life, but trying to look for, you know, any sort of life that would use different building blocks or maybe behave in a different way. And we're also trying to bring as many multiple independent tests for life. So maybe we'll look for, say, amino acids and the distribution of amino acids that might not be Earth-like, but it will certainly be different from any abionic chemistry that could exist there. That's one test. And we'll do a few other chemical tests, but then we'll also do a morphology test, right? Looking for cells. We would also do a more advanced metabolic test to see what kind of food they're eating. And then we would map that all to what we call the provenance of the sample, like look at the geochemistry in the environment. Let's say that we find, oh, it looks like there's a methanogen there. A methanogen is something that eats CO2 and poops out methane. Well, is that reaction favorable in these conditions? Because it's not at certain pHs. Let's compare it to that. Let's try to check ourselves as much as we can. So I'm not answering your question yet, Dave. I'm getting to it. So we don't want to make the same mistakes as Viking. We really want to be sure when we do find life that it's not a false positive. Now let's say that we find life that's there. If it is microbial, presumably we will find it with the first mission we send, but hopefully we would send one or more follow-on missions, because once we detect, let's say it's a microbe, well, okay, now we know what size it is, so we know what kind of microscope to send next. Now we know that it's a methanogen, so it's pooping out methane. All right, great. So we're going to send very specific chemical sensors next time that are just focused on understanding that metabolism and maybe looking for what kind of DNA, if it has DNA, that would code for that kind of metabolism. So there would be more specific tests we'd run next time. But you bring up a good point. What if we find a squid or a series of squid? And what if they try to communicate with us? What then? I cannot wait for that kind of problem. That would be the best problem to have. And one thing that we are finding as we start to engage in this life question and the search for life question is we need to engage all aspects of humanity. That includes reaching out to, theologians. That includes reaching out to microbiologists, ecologists, people who are studying all sorts of aspects of how life interacts with its environment and intelligent life as well. And so that would be a conversation where I think NASA would probably do an all stop until we really engage with those key stakeholders in the community who can say, all right, this is the best way to proceed. But we would certainly want to minimize impact to that life form or that environment as much as we possibly could. But we're not going to know if we don't go. And there is some inherent risk in that. And I think we all have to accept that at some level. So that's the best answer I can give.
Morgan, have you ever seen a science fiction movie called The Europa Report?
I haven't seen it yet. I've heard about it, though. It's kind of like Blair Witch Project meets Apollo 13, right?
No, I mean, half the movie is about getting to Europa. The other half is there. And I think you might enjoy it, especially with your squid comment.
Yeah, there is.
You have to sit through a long time to get to the last 30 interesting scenes.
That I was kind of warned about that. And when it comes to sci-fi movies, there's some that I absolutely love, right? Like The Martian. Andy Weir did such a good job of trying to get most of the science right that there's only one point in that movie where I throw my hands up and go, God, that would never happen because of physics, but yeah, so I should. You know what, Don? I'm going to watch that movie.
It's not a great movie. It's a good movie. It's not great, but Dave's question was interesting because Arthur Clarke wrote the book 2001.
Yes, he did.
And the follow-up novel was 2010. And at the end of 2010, the creators of the monolith sent a message to Earth. They said, "All these worlds are yours except Europa. Do not go to Europa." That was an amazing movie too.
And I don't know if you know this, but so the Europa Clipper mission has a very long history. It was actually proposed a long, long time ago. I think it was, I think 30 years ago, something like that. There's a book about it called The Mission. But during one of those initial science team meetings where they were talking about this, Arthur C. Clarke dialed in and he gave us permission to land on Europa.
Wonderful.
So we did go to the source, and this was before my time. I think I was still a student at this point, but I have a colleague, Cynthia Phillips, who loves to tell that story because she was there at that meeting. And it was just so neat to see this blending of science fiction and becoming a reality with being able to actually touch and explore these worlds.
Yeah, yeah. Well, this is the most science fiction oriented presentation we've had, I think. So
Remember
Well,
now,
I'm-
science fiction often becomes science fact.
Yeah, what is it that Lori Glaze, who's our NASA, I forget her official title. She used to be our associate administrator. Now she works for the Smithsonian. But she did an interview on NPR and she said, she was quoting someone else that I can't remember now, but she said, what was it? That there is nothing that science has done that hasn't been imagined first or something. I'm misquoting her terribly, but the point is a lot of these things happen in science fiction and then we make them a reality. Things like the tricorder, right? We're working on being able to study what something is made of without touching it from very far away. Like all of these types of things are becoming a reality, which is really cool.
I'm hoping your presentation is giving some ideas to, if you notice someone on the Zoom screen here labeled Crypt, do you see Crypt?
I do.
That's Jack McDevitt. He is a world-renowned science fiction author with how many? 30 novels, Jack? Is that right? Oh, you're muted, Jack. On mute. You're muted.
Someone unmute Jack.
You have to unmute. Anyway, yeah, he has had many science fiction novels published and science and short stories.
If you ever need a consultant, let me know. I'll work pro bono for this, just for the joy of doing it.
You got to unmute Jack somehow.
Oh no, Jack, we can't hear you. Can we unmute Jack?
I can't. He has to do it. Lower left. Go to your lower left button. The little microphone. Click on that. Lower left. The little microphone. Click on it to unmute. I can't unmute him. I can only ask him to. Anyway, I think you're probably giving him some food for thought here. The lower left corner of the screen, a little microphone.
And if anyone does have any follow-on questions, I'll put my email in the chat.
Okay, yeah, I'll copy all the links.
Muted. Looks like he's unmuted now.
There, Jack. Yeah.
Yeah, I'm good. Thank you.
Hi, Jack.
Hi, Morgan. How are you?
I'm great.
I was going to ask you one time. I think you've already answered this question, but I was wondering while you're going through this stuff, what there is that is possible that you might find out there on one of these moons that would most shock you.
That would most shock me.
Or
I think it would
surprise you.
be. I think it would be life in the liquid methane and ethane seas of Titan. So Titan has a global liquid water ocean deep down in its interior, but it's that liquid on the surface that, as a chemist, to me is so fascinating because it is a non-polar solvent and it's really cold. Those two things, I think, are bad for life because water is a polar solvent. Lots of charged big molecules can dissolve in water because it's polar. If you remember, like, oh wait, I have a chemistry set. Hang on. Of course I have one of these. Okay, so I'm gonna make a water molecule real quick here. Let's see, where's my oxygen? Or I could just hold them up. Okay, so here's oxygen and here are the hydrogens, right? So here's water, right? And so the butt side, the oxygen side of water is a little bit negatively charged, and the hydrogen arms are a little bit positive, right? Because the oxygen sort of sucks the electrons closer to it. And so whenever you have large molecules that are in liquid water, depending on if the molecule has a charge or not, the water molecules will sort of sidle up, like the oxygens will sort of get closer to it, or the hydrogens will, and they help keep those big molecules in solution. This is why we can have big molecules like DNA and proteins and these things that are like 10,000 Daltons. They're like huge molecules, right? In a non-polar solvent, that gets harder to do. And especially if you cool it down. It's like, if you try to dissolve sugar in coffee, you get a lot more sugar in hot coffee than you do in iced coffee, right? And it's just because of thermodynamics. Cold things just crash out. They don't stay in liquid. And so I would be really surprised if we were to find life in those liquid hydrocarbon lakes, just because I can't figure out a way chemically to get big molecules that would store information like DNA and proteins. I can't get big molecules to like stay in the liquid phase. So instead, this is my theory. And Jack, if you write a book about this, I want to be credited. Okay. My theory is like, who says a cell has to be this big, right? What if you could envision like one lake on Titan, the whole thing could just be one big cell, right? You could have like the cell wall would be the bottom of the lake where all of the stuff, all of the juicy bits are crashing out. All those molecules are down there. And then maybe it just coats the whole lake. And that's one equivalent of like a giant cell. But I don't have any experiments to prove it. And that's just my wacky theory. I'm not speaking as a NASA scientist now, just as like a really enthusiastic chemist.
Morgan,
Yes.
that's not as wild as you would think. Seem to remember something years ago, Precambrian life. They found evidence of a gigantic animal, roughly a meter in size, that was single-celled.
Ooh.
The entire critter was basically protoplasm with a nucleus.
Huh. Okay. Cool.
I wish I could remember where I read it.
Well, if you happen to find it again, send that along because that would be really fascinating. I don't know how we would replicate that in the lab. That would take a lot of liquid nitrogen.
Yes,
Safety would probably get a little upset with me. They were very upset with us just condensing like this much liquid methane because, that's basically you get a flame near there and it's just, you're going to have a bad time. So that's interesting, Dave. Cool. See, I learned something too. This is why I love giving talks like this. I always seem to learn something new.
Well, Morgan, if there's no other questions or discussion, I think we just all really want to thank you for a great talk and really engaging discussion. So
That was
thank
great.
you very, very
That was
much.
great, yeah.
Well, thank you so much for the invitation. And yeah, I get more. Oh, thank you so much. I get more emails in a day than I can answer in a day. But if you do have follow-on questions, reach out. And it may take me a weekend or two, but I will write you back. So thank you so much for taking the time. And thanks for being so engaging. You guys all asked really, really good questions.
Thank you so much for being our guest.
Yeah, thank you, Morgan. Bye.
If you need more guests, let me know. I know a couple of cool scientists and engineers that would be happy to
That
lay
is
some
music to
additional
Bruce's
knowledge.
ears.
Oh,
You're gonna regret saying that.
Be
Challenge
careful what
accepted.
you wish for.
Excellent.
Thank you again.
Take care. Have a great rest of your week.
Thank you.
Clear skies. See you.
Wow.